Okay, welcome back to the physics class, my dear students. So in the previous class, I was discussing regarding the derivation of equivalent focal length of combination of two thin lenses which are in contact with each other. So that there even I shown you the equivalent focal length formula, that is 1 by f is equal to 1 by f1 plus 1 by f2. So that is we obtained by just combining two thin convex lenses. Even we can get the same just by combining of two concave lenses, and even I said you that we can obtain the same thing just by combining of one convex lens and one concave lens. And I just show you the three different cases. What happens if the focal length of one lens becomes equal to the focal length of another lens, as well as even I just show you what happens if f1 is greater than f2 and f1 is less than f2. With all these cases, we just came to the conclusion that the combination of these two lenses are very much useful in application of optical instruments. So whereas when we come towards an optical instruments, there are so many optical instruments like magnifying lens, said to be the simple microscope. Next one is compound microscope, as well as telescope, refracting and reflecting telescopes. See, we have a number of optical instruments that we can observe in our surroundings. So that whereas to know how the image is formed, and how the image is formed by this kind of telescopes and by this kind of optical instruments, we should know that the combination of lenses. So just to be derived with that, we should know some of the simple ray diagrams which were obtained by using the concave and also the convex lens. So I will just show you the main ray terminology, or what I can say that how the rays which are going to refract when they are going to form the convex lens as well as concave lens. Now let us see the ray diagrams which are related to the convex lens and concave lens. See my dear students, now I will just show you the ray diagrams. Whereas these ray diagrams are not, they are not going to ask you any question, that is what you call an examination. So but to understand the image formation by the combination of lenses, the image formation by the optical instrument, that is said to be simple microscope and compound microscope, we need to know the ray diagrams formation by convex and formed by convex and concave lens, formed by convex and concave lens. Yes. Yes. See my dear students, here I am just going to update you the things. I am using the convex lens first. Suppose you can consider a convex lens which is having a principal axis and also the optic center. See, it is having the center of curvature and focus on both the sides. But towards that is the direction. Incidentally, I am not going to represent anything, but to this direction, that is what towards the image formation side, I am just representing the focus and center of curvature. If I just incident a parallel beam of light which is parallel to the principal axis, see I am repeating again. If I incident a parallel beam of light parallel to the principal axis, after refraction it passes through the principal focus. You should remember this. As well as I am just going to show you another one ray diagram, so three rays I am just explaining it over here. So here it is having a focus and also it is having center of curvature. Here also I have shown you the focus and center of curvature. Suppose if the ray of light is going to incident, from the principal focus, so after refraction, the ray is going to emerge out parallel to the principal axis. So both that is what vice versa is, so that the parallel beam of light, if it incident on the lens, it refracts to the principal focus. Similarly, if the ray which is going to incident from the focus, it refracts parallel to the principal axis. Even you have studied this in your class. This is what in your 10th class. And I am using another one ray. This is an optic center. If I just incident a ray of light, a ray of light towards an optic center, so at this point it doesn't undergo any refraction and it passes out without any refraction. So these three are the rays that which I am using for explaining the image formation by the optical instruments. Keep in your mind, I am using these three different rays for explaining the image formation by the optical instruments. As well as this is for the convex lens, even we can write the same thing by using the concave lens. So I already said you that convex lens is the one which always forms real and inverted images only in one case, one single case, when the object is placed between the optic center and principal focus, then only we can observe the direct and partial image. Similarly, concave lens is the one which always forms act and virtual images. So let us see how the three rays are going to behave in case of concave lens. So we should not write this concave lens with this much of thickness. It should be a very less thickness. Yes. So it is having its optic center and principal axis. See here, dear students, I am writing the principal focus and the center of curvature. If a parallel beam of light incident on the concave lens, you know that concave lens is a diverging lens. It refracts and diverges the incident beam of light. It means if I just extend this refracted ray, it is going to meet at principal focus. Right? It means the ray appears to be coming from the principal focus. So it is going to diverge, but this dotted line represents that this ray is not exactly going to meet anywhere, so that this concave lens always forms virtual image. And if I just consider the concave lens again, which is having an optic center, so it is having a principal focus and center of curvature. It is having a principal focus and center of curvature. Suppose if I incident a ray of light, see here, what I am doing, if I just incident a ray of light through the principal focus. See, here when we come towards the discussion in this concave lens case, when we are going to incident a ray of light through the focus, it means you can observe, so I am just going to incident a ray of light towards the focus, right? See here, my ray is exactly towards the focus. So what happens after refraction? It emerges up parallel to the principal axis. So whereas now I am using the third case. Whereas third case is again similar to that of a convex lens. So that here we have optic center. If the ray of light incident to the point of optic center, it passes out without refraction. So I just showed you the three ray diagrams. So it exactly explains you how the ray of light are going to undergo the refraction when they are parallel to the principal axis, when they are falling towards the optic center, and when they are going to incident from the principal focus. Now let us see the ray diagrams for the different position of an object by convex lens. So by concave lens, that you have studied in 10th class also. Even for the convex lens also you have studied in your 10th class. But now I am just explaining you. I am just going to explain you the image formation by the convex lens for the different position of object. Now let us see one by one. Okay, here you can observe. I just considered a convex lens. So which is having optic center. So here I am just going to incident a parallel beam of light which is parallel to the principal axis. You know that already from the terminology that always when the parallel beam of light falls on the convex lens, it should refract and passes through the principal focus. Right? See, where is the object? Consider that the object is at infinity. Where the image is formed? Image is formed at C rather than writing like this. I will just note it down. is the object? Object is at infinity. And where is the image? Image is found at principal focus. What is the nature of the image? See here, the nature of the image is point sized. So that it is the point, the size of the object is reduced. So it is a point sized. Not only the point sized, you can say that it is diminished. Diminished. So my dear students, observe carefully that after refraction, these rays are going to meet exactly at a point. If the rays are going to meet at a point, then we can say that the formed image is real. Right? And if real we are writing, we should write exactly that the image is inverted. So real inverted point size image is formed by the convex lens when the object is placed at infinity. And now let us see this magnification. See my dear students, whereas the where is object is an infinity, whereas image is a principal focus, it means focal length. So what is U? U is infinity, V is F. So V is F and U is infinity. Anything by infinity is 0. So that the magnification is very less. Magnification is point size. So I already said that the magnification is very less in this case. So now let us move towards the discussion of next position of an object. Again I am going to write the same lens with an optic center. So it is having principal focus, center of curvature. I am writing the principal focus and center of curvature on both the sides. Now I am going to place an object at center of curvature. So where is the object? Object is at center of curvature. You observe the ray diagram. I am using two different rays. One is a parallel beam of light. When it falls on the convex lens, it refracts and passes through the principal focus. And again to explain, I am using another one ray, that is what the ray which is passing through the optic center. So my dear students, where is the image formed? The image is formed at the center of curvature. So the image is also formed at the center of curvature. Then what is the nature of image? Observe that after refraction, the rays are going to meet. It means the formed image is said to be, the image which is formed is called as real image. Observe it carefully. See, let us say whether it is inverted or erect. So actually the object is in this way, whereas the image has been inverted. So that I can say that the image is real inverted. And let us see whether it is magnified, diminished or same size. See, the size of the object and image both are same. So that the real, inverted and same size image is formed when the object is placed at the center of curvature. Now let us see what happens to the magnification. See my dear students, the distance between the optic center and the center of curvature is called as radius of curvature, and the distance between the center of curvature and object is optic center is called as radius of curvature, whereas object distance is also r, image distance is also r. So it means r by r is equal to 1. So that the magnification is equal to 1 in case when the object is placed at center of curvature. This is one case. Hope you are all writing. Okay. Now let us see another case. So I am just considering a convex lens with a principal axis and optic center. I am going to write the principal focus, center of curvature, principal focus and center of curvature. Now I am going to place an object in between C and F. Where I place the object is in between C and F. Now let us see where will the image is going to form. And the distance between the object and this is said to be the object distance U. See dear students, I am using one ray that is said to be the parallel beam of light which is going to fall on the convex lens. What happens after refraction? It passes to the principal focus. Similarly, I am using another one ray, whereas the ray is said to be the ray which passes through the optic center. When the ray passes through the optic center, it passes out without diffraction. It passes out without diffraction. See here, you can observe that this is a point of coincidence where the image is formed. So that here you can observe that the image is formed. The distance between the optic center and the image is called as image distance, represented by V. Observe carefully, where is image is formed? Image is formed beyond C. Image is formed beyond C. Right, image is formed beyond C. What is the nature of an image? Observe carefully. After diffraction, rays of light are going to meet at a point. So we can say that the real image is formed. As well as the image is inverted. So here inverted. Let us see whether it is diminished or enlarged. So that the size of the object is enlarged. So that write it as enlarged. Yes, this is the nature of image. Now we can observe that V is larger compared to that of U. So V is greater than U. If V is greater than U, magnification becomes greater than 1. So in this case, we will get the magnification which is greater than 1. So hope you got this. Now let us move to the next other 3 cases. Okay, this is said to be the optic center, right? So it is having principal focus, center of curvature, principal focus and center of curvature. You can observe, my dear students. Now I am placing an object beyond center of curvature. So I am going to place an object beyond center of curvature. Where is the object? Object is beyond center of curvature. That is C. And now the distance between the object and the optic center is called as object distance, represented by U. Now a parallel beam of light is going to incident on the convex lens. When a parallel beam of light incident on the convex lens, after diffraction, it passes through the principal focus. And to explain, I am using another ray so that the ray which is going to pass through the optic center. So that after diffraction, it passes out without refraction. It passes out without refraction, so that it is a point at which the 2 rays are going to meet. So here is the image formed. The distance between the object and the image is called as image distance V. Observe it very carefully that where is the image formed? Image is formed between F and C. So image is formed between F and C. Now let us define the nature of the image. Here the rays after diffraction, they are meeting at that point. So we can say that the image formed is real. And let us observe whether it is inverted or erect. Yes, exactly it is inverted upside down. So that real inverted image is formed. See, let us see the size. The size of the object is greater than the size of the image. It means the size of the image is diminished. Yes. Now, see which one is greater here? Object distance is greater than image distance. If the object distance is greater than image distance, so that is what we will get the magnification less than 1. So this is one of the case which is reverse to that of the case that we discussed earlier. Now let us discuss other 2 cases which are present. I am using a convex lens with optic center, principal focus and also the center of curvature. Dear students, I am going to place an object exactly at principal focus. Where is the object? Object is at principal focus. So the what happens now, let us observe. I am using parallel beam of light which is going to fall on the lens. When the parallel beam of light fall on the lens, it undergoes diffraction and passes through the principal focus. And I am using another one ray. So after the ray which is passing through the optic center. It does not undergo refraction and it passes as it is. So you can observe these two rays are the two, that is what the two refracted rays are parallel to each other. It means the parallel rays, see the parallel rays never intersect, never meet each other. So that where is the image formed? Image is formed at infinity. Image is formed at infinity because they are not going to meet anywhere. So that image is formed at infinity. My dear students, I said that the convex lens is the one which always forms a real. If there is a real, it always forms an inverted image. So here the size of the object is like this, whereas here we can observe the enlarged image. Enlarged image. Now you can see that the object distance is focal length, the image distance is infinity. Right? So that infinity divided by f. So I can say that the magnification is very large. Very large because we are just writing it as infinity. It means the magnification is very large in case when the object is placed at principal focus. Now the last case we are discussing, that is what is special case for convex lens. Why? Because in this special case the convex lens is going to form an virtual image. So I am showing you how to do that. I am going to write the convex lens here. So it is having an optic center, principal focus, center of curvature. These are principal focus and center of curvature. Now I am going to place an object between optic center and principal focus. Where is the object? Object is between principal focus and optic center. Anywhere between F and O. Now let us incident a parallel beam of light which is parallel to the principal axis. So after refraction, it passes through the principal focus. And I am using another one ray, that ray which is passing through the optic center, it passes without undergoing refraction. We can observe this, these two rays are diverging rays. So the divergent rays, they never meet each other. But if I just extend it back, so they meet at some point. So that you can observe that the distance between these two things is objective distance, and the distance between the image and the optic center is called as image distance B. Whereas here the image distance is greater than the object distance. Where the image is formed beyond C, somewhere beyond the lens. The image is formed beyond the lens. What is the nature of the image? So this is erect, right? This is erect because the rays of light are not going to meet after refraction. These rays are not meet at a point. They are not going to meet at a point. We just assume that they are coming from a point, so that they are not exactly meeting at a point. So that time is called as virtual. If we have a virtual, we will have a base erect. Yes, it's right. So the image is also erect as that of the object, but the size is enlarged. This is a special place of convex lens. Now let us see, V is greater than U. V is greater than U, magnification is greater than 1. This is about how the convex lens is going to form the image. So why I just shown you the ray diagrams? Why? Because while we are discussing the optical instruments, so by the time we use the lenses, so that then we should write so many ray diagrams to understand that we should know first how the ray diagram or how the images are formed for the different position of an object in case of convex lens. With this, now I am moving towards the discussion of optical instruments. Dear students, to know the working principles and also to reduce the linear magnification and angular magnification in case of optical instrument, we should know what is least distance of distinct vision. Least distance of distinct vision. Whereas this least distance of distinct vision is represented by the symbol capital D. What is this least distance of distinct vision? Suppose, my dear students, if I just ask you to place this finger exactly in the middle of the two eyes, which is very close to you. Suppose if you place the finger very close to you, such that, otherwise if you place your finger very close to your eye, that is what exactly in mid of the two eyes, so you are not able to see, the clear image of that finger. So sometimes you may observe that the blurred image, sometimes you may observe the two or three images, so that is what you can observe that the two, this is what double images you are observing. So why this is going to happen? So my dear students, so two for every human being, so that the eye is having a own capability to see the object clearly without strain. So that distance is said to be the least distance of distinct vision. So then what is that? How to define? See my dear students, it is defined as, it is the minimum distance. It is the minimum distance. See, actually, this minimum distance is from the eye, right? You should be very careful. This minimum distance is from the eye. The minimum distance from the eye to where? Why? Actually, why we are using? Wait. At which the object can be seen. Sorry for the disturbance. It is a minimum distance from the eye at which the object can be seen clearly without any strain. See, for normal human hand, the least distance of distinct vision is V is equal to 25 centimeter. Keeping your mind and repeating again. So that it is a minimum distance from the eye at which the object can be seen clearly without any strain. Suppose if you place an object very far away from you so that you cannot see it very clearly by the time, you should just want to observe it just by applying a large amount of force on your that is what eye muscles. So that my dear students, what I am saying here, so it is because you know already when you were studying in the 10th class, you might have studied about human eye. So in that human eye you studied about ciliary muscles, right? So whereas they should that is what they should expand or contract depending upon the brightness and also depending upon the position of the object. So here the least distance is the minimum distance from the eye to see the object very clearly. To see the object clearly. Suppose if you place it in front of the eye, so it's not possible to see the object clearly. So that the minimum distance of an object from the eye, so that object can be seen very clearly without any strain. This is the least distance for normal eye. That least distance of distinct vision is about 25 centimeter. Hope you got the definition for least distance of distinct vision. Now let us go towards the definition of optical instruments. What is an optical instrument? See my dear students, when we come towards this optical instruments, we have simple microscope, we have compound microscope, we have astronomical telescope, we have refracting telescope, we have reflecting telescope. All those things can be studied under this optical instruments. Today, first I am using the simple microscope. What is this simple microscope? Dear students, it is an optical instrument, right? So it is an optical instrument. Why we are used to magnify. We use it to see the magnified images. Magnified images. See, I am repeating again. So, what is this simple microscope? So, simple microscope is simply a convex lens, or even you can say that magnified lens. So, in your daily life, you might have observe the magnifying lens, whereas that simple microscope is said to be the magnifying lens. Other simple microscope is also said to be a simple convex lens. Whereas that simple microscope is an optical instrument which is used to see the magnified images. Example, convex lens. Example, magnifying glass. That is magnifying lens. So you can easily write here. This was the example. Magnifying lens. Yes. Then, now let us discuss the expression for linear magnification formed by the simple microscope, and also let us see the working principle of this simple microscope when the image is formed at the least distance of distinct vision. See my dear students, take down the heading. So that after this, take down the heading. Give the working principle of simple microscope when the final image is formed at a least distance of distinct vision, and hence obtain expression for linear magnification. Hope you write this heading. So hope you write this. Hope you return this. Right? Okay, now let us move towards the working principle and also the image formation. Now let us move towards the working principle. Please students, as I said in the ending, so we should discuss the working principle and also we should deduce the expression for which one? Linear magnification for the convex lens for the simple microscope when the image is formed at least distance of distinct vision. So I am just using a convex lens here. So this is important diagram, red diagram, so you should write it carefully. So here is the optic center, right? Now, observe carefully. I am going to write the principal focus. I am going to write the center of curvature, right? Now, I am placing an object. I am going to place an object, right? Said to be AB. AB is the object placed between optic center and principal focus. See, now let us observe the ray diagram. So here we have again the principal focus and the center of curvature. Now from the object, a parallel beam of light is going to incident. When a parallel beam of light is going to incident on the convex lens, it undergoes refraction and passes through the principal focus. Similarly, I want another one way to explain this. I am using a ray which is passing through the optic center. So when a ray which is passing through the optic center, it does not undergo refraction, but it passes out from the same point. So you can observe the two rays. The two rays are diverging rays. The two refracted rays are diverging rays. They are not going to meet anywhere. So if I just extrapolate it, this, they are going to meet at some point, so that the image is formed at this position. Whereas this is said to be the image, I am going to give the name as A dash, B dash. Observe that the distance between the object AB and the optic center is called object distance, represented as U. And the distance between the image and the optic center is called as the image distance, represented by V. Okay students, now let us name all the terms which comes under this diagram. So here the observables. Okay, now what is AB? AB is an object. In this image is at A dash, B dash is called as image. What is U? It is an object distance. Then what is V? V is equal to D. See my dear students, I am calling V is equal to D. See, observe an image very clearly, the image should be at least distance of distinct division. Then this image is at least distance of distinct division, so that's called as the image distance at least distance of distinct division, clear vision. Right. Yes, almost we come to the points. Now let us write the working principle, my dear students. What is the working principle then? What exactly the working principle? See, where the object is placed. When the object is placed between the optic center and the principal focus, the image is formed at a least distance of distinct vision. The image is formed at least distance of distinct vision. So whereas the image is erect, image is magnified, image is virtual. So dear students, you should note all these things in the working principle. Okay, now let us write the working principle. I am just writing when the object is placed between optics and principal focus and optic center, what kind of image is formed? Erect, virtual and enlarged or magnified image is formed at where exactly it is formed at least distance of distinct vision. This is the working principle of simple microscope. Now let us move for the expression for linear magnification. This also comes under the simple microscope. This also comes in simple microscope. See my students. Let us move for the expression for linear magnification. We know that 1 by f can be written as 1 by v minus 1 by u. You know this formula, right? 1 by f is equal to 1 by v minus 1 by u. So my dear students, I might take it as equation number 1. So to reduce my expression, I am just multiplying this equation on both the sides by object image distance v. Multiply 1 by v on both the sides. What will happen now? V by f is equal to v by v minus v by u, right? So here v by f is equal to v by v is 1 minus v by u. My dear students, you know that the magnification m can be written as v by u. So here v by u is can be written as m. So v by f is equal to 1 minus m. See, I am interchanging these two terms. I am shifting these two terms. So if minus m come to this side, it becomes plus m. 1 is there itself. So if plus v by f comes to that side, it becomes minus v by f. Almost all will come to the end of this derivation. So you can observe that. What is this? Image distance. The image distance is this distance of distinct division. So that I am continuing this. So m is equal to 1 minus d by f. Why? Because v is equal to d. Right. Where is this formed? It is formed at this distance of distinct division. But still we have not applied the sign convention. According to sign convention, see here direction of incident ray is taken as negative. Whereas we are measuring the image distance in opposite direction of incident ray. Incident ray is along this direction, whereas I am measuring V in opposite direction. So that V is equal to minus D. Therefore, what happens to this formula? Therefore, M is equal to 1. D becomes minus D. So that minus into minus is plus D divided by M. So this is the required formula for the linear magnification produced by the simple microscope. That is what magnification M is equal to 1 plus D by F, where M is the magnification, D is the least distance of distinct division, and small f is the focal length of given simple microscope. This is about the linear magnification. Dear students, not only this, even we can move for the discussion of angular magnification produced by this simple microscope. So then what is the definition of angular magnification? How the image is formed by the simple microscope and how to calculate the angular magnification. That let us see it in the next class, but now let us define what is the angular magnification. Okay, now let us define it once. So I am just going to define the angular magnification. So you know that the linear magnification is defined as the ratio height of the image to height of the object. So then similarly the linear magnification can be defined as the ratio image distance to the object distance. Then now I am just defining it, the angular magnification. So that I am defining it now. Angular magnification. So my dear students, so angular magnification is also represented by the symbol M. Whereas the formula for this, first I will write the formula theta I divided by theta naught. I represents the image, O represents the object. But in case of linear magnification, we just placed an object in between O and F, and we got the image at least distance of distinct division. But here in this case, it is vice versa. That is what here we are to assume that the object is placed at least distance of distinct division from the eye. So now let us see, let us define it, where theta is the angle, I relates to the image, and O relates to the object. So it is defined as the ratio of what is theta? Theta is an angle. So theta is an angle subtended by the image at I. Subtended by image, because here theta I, right? Subtended by image at I to the angle subtended by theta naught means object. So that angle subtended by object at I, right, at I. If here there is a condition, please be careful for angular magnification. If the object is assumed, to be placed at least distance of distinct division. Yes, this is the definition for angular magnification. Simply we can write M is equal to theta I by theta naught. That is what the ratio angle subtended by the image at the eye to the angle subtended by the object at the eye. If there is an assumption, that is what the object is assumed to be placed at least distance of distinct division. This is about the definition. So, but in the next class, we are just moving towards this derivation of magnification. It is what angular magnification. in case of simple microscope. Today we just discussed the linear magnification in case of simple microscope, but in the next class let us move towards the discussion of angular magnification in case of simple microscope. Only a bit difference is there between the angular magnification and the linear magnification derivation, but there we used to place an object between F and O, that is principal focus and the optic center, but here we are going to place an object exactly at least distance of distinct vision. So thank you my dear students. Please take down the notes. At the same day itself, go through the working of each and every concept. Thank you.